Greetings, friends. Word problems, ugh. Linear functions, ugh. Alright, let's see if we can attack a couple of these things. Okay, humans, let's see what we've got here. What I recommend is that you pause the video and see if you can do this yourself. So go ahead and pause the video. I'm going to work it out. Here we go. The annual household cost of a telephone service in the United States increased relatively constant, at a relatively constant rate. So here we are. We have a constant rate of $27.80 per year in between these years. In 2001, we're for sure that the cost was $914. Let's let that marinate. Maybe read it again. Okay, so if you've read it again, maybe you found that the annual cost is equal to this idea of an increase, $27.80. It increases every year, but you have to start with some price, and then you are increasing this much every year after. So if we learned, like it says in the last sentence of this problem, that in 2001 the cost was $914, knowing that it increased $27.80 every year, and it would have some startup cost. Well, if there's been 20 years since 1981 until 2001, maybe we can put in a 20 here for the number of years that it had to increase this $27.80. And then if we subtract that, we'll be able to find out where we started. 20 times $27.80, I believe, is that. And then we subtract 556 from both sides, and it looks like 358 is equal to B, because it was 20 years prior. Now, for B, if we wanted to represent an equation that made this specific to the number of years since 1981, we still recognize the annual cost as a function of this increase in price, this constant increase in price, times x, which in this case represents the number of years since 1981. And now we have the number that we found to be the initial startup cost of $358. Of course, to put it more simply, we can use a single variable c, or the cost is equal to this $27.80 times x, the number of years since 1981, plus 358. And you would imagine if you put in a 20 here for x, and multiply that times 27.8, and add 358, you would go back to this idea of 914. If you put a 20 there, because 20 years after would be 2001, and we already learned that the cost was $914. And lastly, let's look at C. If we're trying to find the household cost for a telephone service in 2000, well, the number of years since 1981, 2000, it looks like it's been 19 years. So we've got our cost function. Our cost is equal to $27.80 times the number of years since 1981, and you add 358. So it looks like you're just substituting in a 19 here for x, multiply the 27.80 times 19, and add that with 358. And it looks like the answer, according to my calculations, is this number here, and that's your cost. Hopefully that makes sense. moving on. Here's a problem that's very similar. Perhaps you can pause the video, try this one yourself, reference the one before, and see if you can come about a good answer. Pause it. Okay, here we're going to do some work with this here. From 1990 to 2001, the number of airports in the United States increased at a relatively constant rate, 175 airports in every year. So a constant rate of change, slope, right? Constant increase at 175 per year. It tells you that there are this many airports in this year. So it's a little data point you got going on. If this a constant rate, here's a line, a linear function, which describes a constant rate of change. Right there, we'll call this blue. That describes a constant rate of change, your slope, which might be having something to do with this per year, how it's constantly changing. And I think the number of airports depends on the year that it is. The number of airports depends on the number of years. So maybe we can find an initial truth about our function here. And that initial truth has to do with the number of airports in 1990. All I know is about 2001. And I know that the number of airports was 19,306. After having changed 175 airports for 11 years, it ended up with this number over here. But it had to start somewhere. So let's do the math. And it looks like this number is 1925 plus B equals 19,306. And if we subtract 19,306 and we subtract 1925, it looks like the answer is 17,381. That's how many airports you started with in 1990. So for B, it's asking you to write an equation that gives the number of U.S. airports as a function of the number of years since 1990. So the number of airports, we can call it A, we can call it Y, it doesn't matter. I'll use A. The number of airports changes 175 every year since 1990. And it began in 1990 with 17,381. So there you have it. Lastly, we've got C, and we're going to find the year which the number of airports will reach, or did reach, 19,200. Well, the number of airports is given by A, so if we want that number to be 19,200, we can say that's equal to the same rate of change multiplying the number of years since 1990 plus 17,381. To try to isolate x, it looks like we would subtract, that's a big subtraction sign, subtract 17,381 from both sides. And we've got 1819 equals 175t. And we divide 175 from both sides, and you'll end up with 10.4t. So in what year? Well, if all of this mess started in 1990, and it takes 10 years to get to this number, well, 10.4, you add 10.4 from 1990, and you're somewhere in the year 2000. So what year? I think it's 2000. These type of problems take a little practice, but I think once you do a couple, it starts to make sense. The process is sort of similar with all of these problems. It's just a matter of putting the right pieces in place. Good luck with your mathematical endeavors. You can try 51 in the book, which is similar to 50 and 52, the ones we tried, and you can get practice with practice worksheets B and C. Let me know if you have any questions. Toodles.